Hey, good morning, everybody. This is Mr. Ainsworth, and we're going to get into some algorithms to solve TSPs, the famous traveling salesman problems, okay? And in this lesson here, which covers sections 4 and 5, we're going to investigate the first two algorithms right here, what's called the brute force and the nearest neighbor algorithm, also known as go cheap, okay? And the brute force is what's called the exhaustive search. Okay, so we're going to explore these two here through some examples. So go ahead and turn that page and we'll get right into it. In the later sections, we'll take a look at the third and fourth algorithms, but not in this lesson, okay? That's later on. All right, so in sections 4 and 5, which is I combined them, we're going to be taking a look at the first two algorithms to solve the TSP problems, okay? Traveling salesperson problem, okay? TSP. All right, that's our acronym right there. Okay, now first strategy was what's called brute force, or what's called the exhaustive search, which is you basically have already done it before. Um, However, we're going to be very specific about it in this lesson right here. What we want to do is make a list of all distinct Hamilton circuits. Okay, all distinct Hamilton circuits. That's where the order is different in each of the circuits. Remember, a Hamilton circuit is where we visit each vertex once and only once. And then we're going to calculate the total weight of each circuit. Obviously, we're going to compare, and then we're going to choose the optimal solution, which is the smallest total weight or the least total weight. And then we'll talk about that, okay? So here we go. We're going to have to pick a starting vertex. Okay, so since I'm teacher, let's start at A. So let's write that down, okay? Let's start at A, vertex A. So this is our starting vertex right here. So we're going to list all distinct Hamilton circuits from A. So we're going to start here. All right, and then we're going to go for it one by one. Okay, so here we go. One thing I can do is I can go in a clockwise manner. That's the first simplest one I could do. So I can go from A to D to C right here and visit C, and then visit B, and then right back to A. Okay, this is a Hamilton circuit where I visit each vertex once and only once. So I can go A to D to C to B, right back to A. And well, then I can reverse that, right? The mirror image, or what's called the reverse, okay, which is basically opposite order. So this one right here becomes A, B, just read it backwards, A, B, C, D, A. So A, B, C, D, A. And what we want to do is calculate the total weight. Now, both of these would be the same because it's just in reverse order. So just look at clockwise here. 15 plus 14 plus 9 plus 13. So 15 plus 14 plus 9 plus 13. All right, and do your addition right here. All right, add them up and you get weight 51. That's your total weight. The question is this the least possible weight or the optimal solution for all possible circuits? And the answer to that question is we don't know yet, all right? You have to exhaust them all. You have to go through all distinct Hamilton circuits. And so the question is, how many are there in K4? So this is a complete graph, which we call K4. So let's recall this. For complete graphs, okay, for complete graphs, the number of distinct Hamilton circuits, okay, Hamilton circuits right there is equal to n minus 1 factorial. All right, since we have n here is equal to 4 right here, we have, well, let's see, it's 4 minus 1 factorial, right? Okay, well, that's 3 factorial, and that's 3 times 2 times 1, that's 6. So we have 6 distinct Hamilton circuits. We have 3 of them, and they're reverses, okay, or they're opposite. The circuits in opposite order, or what's called their mirror image. There's different vocabulary for these things. It all means the same thing. All right, so what we need to do is find 2 more circuits. So there's one. Let's find another one. All right, so instead of going clockwise, well, you could go along the diagonals. Okay, so let's say we go from A to D down to B. So I'll put this one in red. So A, D, and then across to B, and then over to C this way, and then back to A. Okay, let's write that one down. So A, D, B, C, and then back to A. Its mirror image, or the reverse, would be A, C, B, D, A. All right, but what is the weight of that one? So let's calculate it. So 15 plus 16, okay, from D to B is 16, weight 16. So 15 plus 16, and then cross over to C is 9, all right, and back up to A is 12. So what would the total weight of that be? Well, if you add them up, you get 52, okay? Oh, so far the first circuit is better than the second one by 1. Okay, not by much, but by 1. But is that the least weight? I don't know. So you have to calculate the other one, right? And so what we want to do is go the other direction. So instead of going to D first, I'm going to go down to B. So let's see here. I'm going to do it in blue here. So I'm going to travel this way, A to B, and then up to D, and then back down to C, and then to A. Well, that's a different circuit. Okay, so let's talk about that one. So A, B to D, down to C. All right, back to A. It's reverse, which has the same weight. It would be A, C, D, B, A. And what would that be? Well, we're going to go from A to B, that's 13. Up to D, that's 16. Down to C is 14. And then to A, that's 12. All right, add those up, you're going to get 55, okay? So when you exhaust all the different possibilities, which there are only 6 in this case, and you compare their weights, okay, compare these guys. Ooh, I didn't mean to do that. 51, 52, and 55. Well, 51's the least possible weight, right, out of all 6. So we say that that's the optimal circuit. So this one right here, this is optimal. Okay, optimal because it has the least weight. All right, least weight. Cheapest, or you can say the cheapest, the least. Depends on what these numbers mean. I mean, if they're costs, then it's the cheapest. If they're distance, then it's the minimum distance. All right, or the least possible distance. So this one's optimal, OPT. Okay, the first circuit or the mirror image, one of the two, because they're the same order. So the brute force algorithm, let's go through it again, just to review. You make a list of all the possible circuits, starting at one particular vertex. In this case, I started at A. You know, you have to, in your homework, you'll have to read the problem and go with the flow on what they ask you to do. Or if they don't tell you, well, then you just pick a vertex and you list all possible circuits from that particular vertex. Okay, so then you list them all out, calculate the weights for each, and the optimal one is the smallest weight, or the least total weight. The least total weight. Optimal is the least. But here's the deal. The pro for this, there's some pros and cons for every algorithm. It is an optimal algorithm, which means that every time you use the brute force algorithm, it will always find the optimal or the shortest Hamilton circuit. Okay? The shortest circuit meaning that if these were distances, then 51 is the shortest versus 52 and 55. All right, the problem with this is that for complete graphs, okay, or most graphs, as you increase the number of vertices, the number of steps to perform this and the number of circuits that are even possible grow disproportionately larger than the number of new vertices added or the edges added in the graph. Like K, for example, if you let's say if you have a complete graph with 7 vertices and you take a look at K7, all right, and that is 7 minus 1, factorial here, which is equal to 6 factorial. All right, you guys, that is 720 Hamilton circuits. There's no way any one of us can list out 120 distinct Hamilton circuits, calculate their weights, and then compare. I mean, it would take you more than just one class period. It would take you a week, and the probability of making a mistake is probably pretty good. All right, so it's inefficient because you have to list them all out, and that is a problem. That's why computers are necessary. So we need better ways to doing things, or at least different ways to get approximations. All right, it may not be optimal, but sometimes only a good approximation is necessary. All right, it doesn't have to be exact all the time. So let's take a look at strategy 2, which is called nearest neighbor algorithm. Now, nearest neighbor algorithm has another name. It's also called go cheap, and we'll talk about that and why they call it that as we go. But the nearest neighbor algorithm is a very simple one, and it's efficient compared to the first one. So what we're going to do is we're going to start at a designated vertex. Okay, we're going to call that home. And if there is no designated one, we're just going to pick one. All right, like I usually do. I usually pick one. And then uh, in this case, I'm going to pick one right here. Woohoo! Okay, I'm going to start at A. So right here, this is going to be our home base or their starting point. From the starting point, we're going to go to the nearest neighbor, which is the edge with the smallest weight. All right, that's the one we're going to pick. And then from each vertex thereafter, we're going to go to its nearest neighbor, hence the name nearest neighbor algorithm, that hasn't already been visited. And then we're going to continue doing this until we get back to home, all right, which will give our circuit. So get out your red pen, and we're going to highlight in red, okay? And we can easily see the circuit come out. Okay, so here we go. We are going to highlight as we go. We're going to start at A, and we've got to figure out where we're going to go next, right? We're going to go to its nearest neighbor. So pretend these are distances here on the graph. So A is, let's say, 15 miles away from D, and it's 12 miles away from C, and 13 miles away from B right here. Where, what location, vertex, is the closest? What is the nearest neighbor? Okay, if these are like 4 homes. All right, so is D closer? Is C is B? And well, it's pretty darn obvious, right? 12 is smaller than 13 and 15. So what we're going to do is we're going to travel to C first. Why? Because it's our nearest neighbor. 12 is obviously smaller than 13 and 15. So we're going to go to A to C. From there, we have a choice. We have 2 choices. We can either go to B or D. Well, which one's nearer, right? Which one's closer? So, 9 versus 14. Well, it's obviously 9 smaller, so you're going to travel to B first. All right. And then, well, I got to travel to every vertex, right? So I can't go back to A because that won't be a Hamilton circuit. So then I'm going to travel up here. Oh, you know what? Yeah, I said that right. So I'm going to travel up here to D. All right. And that's, I have to go there. And then I'm going to come back home. All right. So let's repeat that. So A, C, B, all right, up to D, and then back home. All right, traveling to each vertex once and only once. So let's write down the weight. So from A to C was 12 right here. All right, from C to B is 9. All right, these could be like miles or something like that in terms of distance if they represent distances. And then back to D here, or to D, that's 16 right here. And then to back home, well, that's 15 more. And if you add these up, you get 52. Okay, you get 52. So if there are distances, it kind of makes sense the name nearest neighbor. Go to the closest neighbor right here. If there are costs associated like this, like if this costs $9 to go from C to B, then go cheap makes sense, right? So it has names depending on, or different names depending on the problem that you're solving here. But it's a simple one. And it's got some pros and cons too. What happened to my pros and cons? Oh, they got shifted over to the next page. Okay, so turn to the next page here. So that was a mistake on printing. So the pro is that it's efficient, it's easy to perform, and it's quick. The problem is it's not optimal. Okay, not optimal, which means, all right, it doesn't always guarantee. This is the nearest neighbor here. Nearest neighbor. Sorry for my the printing problem right there. So the nearest neighbor algorithm, it doesn't guarantee the optimal solution. Okay, you can get a good approximation, you can get close, but it doesn't always give you the exact. Okay, so it doesn't guarantee the minimum, all right, or the cheapest circuit. Cheapest circuit. There we go. All right, it can give you an approximation, a decent approximation, but it does, and sometimes it does give you the minimum or the cheapest, but not always. Okay, but it's quick and easy to do because you don't have to list out all possible circuits. That's another pro. In fact, let's say that you don't have to. Another pro would be is that you don't have to list all possible circuits. And that's a good thing because, like I said earlier, um, you'd be happy about that because in most cases the number of possible circuits is large. Okay, like I said up here in in a simple complete graph like with 7 vertices, there's 720 Hamilton circuits. You don't want to list them all. Okay, that's it's inefficient. Okay, and you don't want to do that. So you got to come up with better ways, or at least different ways, to get in an answer, right? Okay, now let's take a look at this. Sometimes you can take a complete graph here. This is K4 again. All right, your complete graph, and you can convert it into a table. A weighted graph may also be represented as a table. Ooh, okay. So what you first have to do, or one of the skills that you need to do, is be able to go back and forth from table to graph, graph to table. All right, and so what we're going to do is we're going to look at the two vertices here and look at their distances between them, or their weights between them, and fill the table. So let's do that. So between A and D, so A and D is 8. All right, so I'm going to put A and D. Edge AD is 8. This is right here. This one's AC right here. A to C. A to C is weight 20. And then A to B. A to B is weight 12 right here. So 12. Let me see, A to A. Well, guess what? There are no loops. Okay, so there's no value there. Okay, there are no loops. So B to B does not exist in a complete graph because they're not allowed. Okay, so no loops from B to B, C to C, no loops. So on the diagonal, there are not going to be any values in the table because no loops are allowed in a complete graph of K4. Now, if it's not complete graph, then you may have a loop, but we're not investigating that here at the moment because you're looking at K4, complete graph with 4 vertices. Now from B to C, well, B to C is right here, weight 20. And then let me see, B to D, B to D, B to D is 15. And then the last one, C to D, C to D is right here at 17. All right. Now let's complete the bottom half. So B to A, well, B to A is right here, it's 12. And we already knew that because it's up here. The order in the letters does not matter. C to A, you can see it in the graph, it's 20. You can see it in the table and in the graph. C to B, well, C to B is already done. It's already right here. It's 20 right here. D to A is the same thing as A to D. It's 8. And B to D is already stated up here. It's 15. And then D to C, well, let me see. C to D is D to C, and that's 17. So there's a couple things that you see in a table representing a complete graph, okay? A couple observations. So number one, let me just highlight something right here. See, the upper half of the table is symmetrical symmetrical in respect to the lower half of the table, okay? And the diagonal is blank because there are no loops, okay? So first observation is that the diagonal is blank, no numbers in there because no loops exist on a complete graph. Okay, let's write that down. So diagonals, okay, are blank, or have, you can say have no values, okay, are blank. Why? Well, no loops exist in a complete graph. So no loops exist in a complete graph. Okay, and also, second observation right here is that it's symmetrical. The blue region is the same as the yellow region in this case because the order in the vertices do not matter. Okay, so second thing is that the upper half is basically the same as the lower half. So upper half of the table, let's say upper half and lower half are the same, are symmetrical, are the same. Why? Because the order of the vertices does not matter. Okay, so the order of the vertices, B to A to B, well, the order doesn't matter, right? It's the same weight. So order of the vertices does not matter. Okay, first basic thing. So now let's switch gears a little bit here, guys. We went from from graph to table. Well, let's reverse it. Let's take a table, complete the graph, and label the graph with its weights, and then use find a circuit here. So here we go. The first thing we're going to do is we're going to draw the complete weighted graph. All right, so here we go. Now, first of all, we're going to draw it. And so let's draw the graph first, and then we will fill in the weights. Okay, so grab your straight edge if you have one. So here we go. So we're going to draw the complete graph here first. So every vertex is connected to every other vertex. This is K5 in this diagram right here. So we're going to connect every vertex with every other vertex. There's 4 edges, and then we have to connect again, another 3, and then another 2, and then 1. Okay, you're looking at a complete weighted graph, which we call K5 because it has 5 vertices. So this is K5. Now let's fill in the weights of the edges. Okay, so from A to B is weight 3. Well, it'd be kind of nice if we label the vertices. So A, B, C, D, and E. So let's just start off with the top vertex right here at A and go clockwise, A, B, C, D, E, and then we could actually fill in the weights. So A to B is weight 3. A to C is 4. A to D is 5. A to E is 6. There we go. And then B to C is 5. And B to D is 7. And B to E, excuse me, yeah, well, I said right. So B to E is 9, excuse me. B to E is 9, so I'm going to put 9 right here, BE. And lastly, we got C to D is 6. And we've got C to E is 8. So this one's 8. And lastly, we got E, D to E right here in this weight 1. All right, so now what you do after you label the vertices, after you label the weights, okay, you got to label the graph first, all right? Okay, so you label the graph with the vertices and weights. Then you follow the directions and you find the Hamilton circuit, the optimal Hamilton circuit, either by brute force or nearest neighbor. Now, for some reason, my directions are on the next page. I had a little printing problem here. So on the next page, it says find the nearest neighbor solution starting at D. So let's write that up here. Okay, apologize for the little printing problem here. So find, all right, like I said, find the nearest neighbor solution. So we're going to use nearest neighbor and we're not going to use brute force here. We're not going to list out all the circuits because there's too many of them. Okay, so K5, that's n minus 1 factorial. So 5 minus 1 was obviously 4 factorial, which is 4 times 3 times 2 times 1. 12 times 2 is 24. So if you're going to do this by brute force, it'd be 24 Hamilton circuits. All right, so scratch that. Too difficult, too time consuming. We're going to use nearest neighbor. So find the nearest neighbor solution. Okay, and we are going to start at D. So nearest neighbor starting at D. So starting at point D. Okay, that's my goal right now. Come on, Ainsworth. I have a little writing issue here. All right, so that's what I want to do. So we're going to start up here. No, not down up there. That's alphabetical. We're going to start down here. Okay, so there's my start. And so here we go. So D to what? Well, I want to go to nearest neighbor, right? The one that's closest. So I can either go to E, which is weight 1, or C, which is weight 6, versus if I go from D to A, that's 5, or D to B, that's 7, right? What's this nearest if these are all distances? Well, it's obviously E, right? So let's cruise up here. Put the sound effects in. All right, so that's I'm going to go to E, and that's weight 1. Where do you want to go next? Well, we can go to A, 6 miles away, versus B, 9 miles away, and C is, ooh, that's 8 miles away. So what's closer? What's nearest? Well, A is nearest, right? 6 is smaller than 9 and 8. All right, so we're going to go to A. So that's 6 more miles. And where we're going to go next? Well, we can't go to D because that's where we started. We don't want to go back home yet. We've got to visit every vertex at least, not at least, but exactly once. So I can either go to B or I can go to C. Well, if I go to C, that's 4 miles away, or I can go to B, that's 3 miles away. So obviously choose the nearest neighbor, right? Okay, so B, that's 3 miles away. All right, and then I can't go back home. Not yet, so I have to go this way. All right, so I have to go to C, which is 5 units, or 5 miles, whatever these represent. And then I visited all the vertices, so now I got to go back home. All right, so plus 6. So if you just count them up, so that's 7, 10, plus 11, 21. So right there, this is my total weight. Okay, and there's my nearest neighbor solution. Nearest neighbor solution for this weighted graph. Okay, do we know it's optimal? No, we'd have to exhaust them all. Okay, which means we'd have to write them all out and then take a look at every single possibility. So, which we're not going to do right at the moment. But it does give us an approximate solution to the problem. There we go. And that's what nearest neighbor gives us right here. It gives us approximate solution to the problem. It may be optimal, it may not be. We really don't know it unless we exhausted every single circuit out of, well, guess what? There's 24 of them. All right, there's actually 12 because their marriages are the same as the 12. So you'd have to find 12 distinct circuits, find their weights, and then compare and see if that's optimal. And I'm not going to do that right at the moment, okay? What now? We're just going to get used to the different methods. Okay. Now in this example here, we have a table which represents a complete weighted graph. All right, if you count the number of vertices, 1, 2, 3, 4, 5, 6, 7. This is K7. So N equals 7 vertices. This is a complete weighted graph. So check this out. So for a complete graph which is K7 right here, the number of distinct Hamilton circuits, that's Hamilton circuits right there, is equal to n minus 1 factorial. Now for this one, it's 7 minus 1 factorial, which is obviously 6 factorial. Now, if you figure what that is, and I'm just going to show you again on the T84 right here, as soon as I get it going right here. If you evaluate that, let's type in 6, hit math, and then go to probability. Oops, one too far. Notice the exclamation mark right there? That's the factorial symbol right there. You don't say 6 exclamation mark. No, you say 6 factorial, and that's number 4. So you hit number 4, and then you hit enter, and you get 720. And that should make sense because 6 times 5 times 4 times 3 times 2 times 1. Let me see, that's 6, 24, 120 times 6 is 720. There's 720 Hamilton circuits here. All right, and that is way, way too many to list them all. All right, there's 360 of them, and they're mirror images, or they're opposites, or they're reverses. So we're not going to list them all. So what we're going to do here is first understand this. Does brute force or the exhaustive search, does that make sense? Is it practical? Okay. And I'm going to say no. Why? Because there's 720 Hamilton circuits here, and we're not going to do that. So what we're going to do is we're going to do something a little bit more efficient. We're going to start at vertex A, and we're going to use nearest neighbor here and find the nearest neighbor solution for this problem. So get your red pen out and highlight the path. So in this one, always highlight, if I can spell, okay, so highlight as you go okay, in red. Okay, and then record the weights. So record weights and then calculate the total. Okay, so here we go. We're going to start at A. So let's find A. It's right here. All right, and then what we're going to do is we're going to highlight it as we go and figure out the nearest neighbor solution. Okay, which is the total weight of the Hamilton circuit starting at A, following the nearest neighbor algorithm. All right, so there's a lot of numbers up here, so you got to compare as you go. So where do I want to go? So if I went to B at 75 versus 50 versus 28 versus 35 versus 15, all right, versus 22. Well, 15 is the smallest or the least weight, so I'm going to travel to F. So let's put some arrows on there. So I'm going to go from A to F, and that's weight 15. But now where do I go? Okay, well, I've got to compare, right? I can go to B for weight 65, or G at 13, or C at 35, D at 30, or E at 40. Well, 13 is the smallest value, so I'm going to cruise up here to G. So that's weight 13. And then I have to go to every vertex, so I can't go back to A because I want to end there. I can go to E for weight 32 versus 29 versus 28 versus 50. Okay, so what do we do? Well, let me see. 28 is smaller than 29, so I'm going to pick 28. So I'm going to cruise over here to C. So to C, that's weight 28. And then where do I go? Well, I can go to B at weight 30, or to A. I don't want to go back to A. I can go to E for weight 48, or I can go to D for 40 here. So what's smallest? Well, I think 30 is the smallest. So I'm going to cruise up here to B. So that's weight 30. Now from B, I can cruise down here at D at that 60, or to E for 80, weight 80, or there's no other choice. So either 60 or 80. Well, 60 sounds smaller than 80, right? So I'm going to cruise down here to D for weight 60. And then I have to visit every vertex once, right? So I can't go back home yet because I haven't visited E. So I got to go visit E. So go to E here and that's weight 20. And then I got to go back home. And when I go back home, that's weight 35. Okay, so back home, because it's a circuit, right? We want a Hamilton circuit, and that's 35 more, so plus 35. And so the total weight would be the sum of all these, right? All right, and if you add them up, all right, you get a total of 201. You should verify that, by the way. So the total weight for this Hamilton circuit and the nearest neighbor solution, this is called the nearest neighbor solution, okay, is 201. Do we know it's optimal? Don't know. There's 720 circuits, right? Or 360, different ones with different weights. And we'd have to list them all out and compare. Okay, so I really don't know if this is optimal, all right? But I do know that I have a solution. So that's good, because sometimes you're only concerned with a solution, just a possible solution, or an approximate one. Approximate, I didn't mean possible, I meant approximate. So, and that's good enough. All right, you just need a flat out possible or approximate solution. So use the efficient method. That gets you one, okay? Because if I asked you to exhaust all these and do all 720 or at least 360 of them, you'd be here all day. And that's not practical, is it? Okay, because we have a life. All right, you got your family, you got your friends, you got your sports, you got your academics. And math is cool, but it's not the only subject. So you can't dedicate, an entire day or a week. This would probably take you a week to solve one problem. Okay, computers are used nowadays. We'd use a computer to actually exhaust that problem, and there are programs, computer programs to actually do that. All right, so what I want you guys to do is try it, okay? So right here, your homework is on the next page. I want you to go for it and then check your work with mine either on Remind or on my website or in class, okay? And I will see you in my next lesson, and we'll get into, we'll get into the other algorithms, okay? All right, but first try your homework, work with your partner, make yourself proud. This is Mr. Ainsworth. I'm out of here. Bye-bye.